So now we're ready to go ahead and get started coding, and then we'll call this just proportional control. Coming up with names is the hardest part of this, honestly, along with drawing alphas. So I'm just going to go ahead and paste in our regular imports here to save some time. The most important thing to note here is this solve IVP. What it's going to be used for is in conjunction with our differential equation. Forgot I had my old homework up. So this here, all of this is a series of differential equations. We're going to be using solve IVP to solve our differential equation, or actually we're going to be using it to integrate our differential equation, which will let us plot it over time. So we can get started right away with this. Our right-hand side of the equation is going to be all this, and then we want to be solving for the change in height over time. So since we're going to be integrating it, we want it to be the difference in height over time, so we can actually get the height as we integrate it. So we're going to have to move over these cross-sectional areas over to the other side. And our inputs are going to be our time, and then, of course, our starting heights. And then we'll actually make that a vector and just unpack it inside of the function here. And then h1, h2, h3 is going to be our vector. Actually, we'll call it I1, high 1, high 2, high 3. And I like to use underscores. Makes me feel like I'm a fancy coder here. And then from there, we can just go ahead and basically put in all the information that we have here. We know that our Qn, or we'll start with our proportionality constant. Well, no, we won't. We'll define that in a second. So our Qn is going to be equal to our proportionality constant, and which we haven't defined yet, we will in a second, times the difference in our h3 set point, which we also haven't defined yet, minus our h3, our height of tank 3, and then our Q12 is going to be the sine of our height 1 minus our height 2 times our alpha. So like I said, we could use one alpha for all these, because in this specific problem we're just going to be using the same alpha. But I'll go ahead and say our alpha 1 times the difference in these heights again. But this time it's going to be the absolute value of the difference in the heights. Again, so we avoid having a negative sign within this term. And then raised to the 1/2. And then same thing for Q2 to 3. I'll actually just copy this, because all we have to do is change which specific variables we're going to be using. So it's the same thing, just with tanks 2 and 3. And then our Q3, our outflow from 3, is going to just be equal to our, sorry, I forgot to change this proportionality constant, our third proportionality constant times our height of tank 3 raised to the 1/2 again. So from here, we want our function to return each of these equations over here. These equations, if it would let me highlight, I think you can see that. These three equations over here. So we have our right-hand side of the equation, and we want to move this constant or this cross-sectional area over to the other side. So we're only solving for the integral of the derivative of height. And we want to return all three of these. So we're going to have our first one is just going to be negative Q12 divided by our cross-sectional area of 1. And then we want to return our, and then I'll break this up just to make it easier to read. We're going to have these three terms, our Qn plus our Q12 minus our Q23. And then all of that is going to be divided by our cross-sectional area of tank 2. And then same thing with the equation for tank 3. I don't know why it's not scrolling. There we go. It's going to be the difference between our tank 2 and the difference, the outflow from tank 2 to 3 minus the outflow from tank 3 by itself. And then, of course, we're going to be dividing by the cross-sectional area one more time. So from here, you can see that we have quite a few variables that we haven't. I'm not sure what happened there. Quite a few variables we haven't defined yet. In this case, we need to define our set point. We need to define each of our heights, and we also need to define our proportionality constants, our cross-sectional areas, and our proportional control. So we can go ahead and start cleaning things up. The first thing I'm going to clean up is these initial heights. I got that a bit backwards. That was just plain mistake. But since we're going to be continuously using this function pretty much and plotting it over the course of time, well, the integral of it over the course of time, we want to use the heights. So outside of the function, we're going to be defining our initial, and then that's going to be our initial input into this, and then letting it run. So we can go ahead and define the proportionality constant, our set point, and our proportional control, our proportional gain, I guess I'll start calling it, our proportionality constants, and then our cross-sectional areas I think we can define as well. So we have Kc is going to be 0.1. Our alpha 1 is going to be 0.1, so our alpha 2 and our alpha 3. And then our cross-sectional areas are again going to be 0.5. Our cross-sectional area 2 is going to be equal to 1 square meter. Actually, I have them written down. I don't know why I'm trying to remember all these. Let me scroll over there. There we go. Now that's easier. And our cross-sectional area 3 is going to be equal to, let's see, 2 square meters. And then we can define our initial heights outside of this. Last thing we need to define is our set point. And that is going to be 4 meters. So let's go ahead and make sure that's all good. Looks like we're good there. Then I'll just space it out a little bit. So I might come back and clean this up at the end, but for now we can leave it like it is. But I might clean it up just to make it a little more condensed and not take up quite so much, so many lines of code. So now we're going to be using this solve IVP function, our initial value solver. But before we do that, we need to define a few more things. We need to define our initial heights, and then we're also going to have to give it the range that we want to simulate this over. So or basically the bounds of integration. So we're going to be giving it, we're going to start at 0, obviously, because we can't start at a negative time. Well, I guess we could. In this case, we're not going to. We're just going to start at time equals 0, and then we need to give it the final time that we want it to go to. So we'll say our time initial is going to be 0. Our time final is going to be, we'll go to 200 seconds. And then our H, I1, actually, no. Yeah, we'll say I1. Our initial height for tank 1 is going to be 0.5 meters. Our initial height for tank 2 is going to be 1 meter. And the initial height for tank 3 is going to be 2 meters. This is actually bothering me a bit. Also, we don't need our notes anymore. But this is actually bothering me a bit. I'm going to go ahead and move a lot of this outside of here. We'll leave our set point and our proportional control constant there. Then we're going to redefine these. And I'm not too sure why I did it this way initially, but we can go ahead and just do it in this form. And I'm writing it like this instead of just setting each of them equal to 0.1, because if we want to change any of these, A, it's nice to have it all in one line, so we don't have to go looking for the other ones. And then B, it's also nice to be able to just come in and change it if we're simulating a different system or something. And we can do the same thing here. And then we can do the same thing here as well with our initial heights. All right, so now we're ready to go ahead and get started using our numerical solver. So at this point, I went ahead and actually just made these into a vector. It's a small thing, but not a huge deal. And then up here, I did forget some parentheses. And another thing I forgot that is extremely important is the absolute value. So if we run this one more time, all right, now we should be good to go, and we can start using the solve IVP function. We're going to be solving our RHS function, our right-hand side of the equation function. We have to provide it, and I forgot that I deleted this, but our initial time is going to be 0. We have to provide it our start and our end times in the form of a scalar, well, 2 scalars, and we're going to just use our Tn and our T final, our time initial and our time final. And then we have to provide it the initial values. So we'll give it the H initial. And then finally, we need to give it a method. And we're going to be using redo, not totally sure on the pronunciation there. And then we want our dense outputs to be true. And we just want the solution here. So we'll go ahead and run that. So now we're good to go. And then we're going to make this into a variable, and we'll just call it our solution here. So we're ready to go ahead and start plotting. We didn't actually need the apostrophes around that, by the way. But anyways, we can go ahead and start plotting. We need to make a t-plot for our time, and then we don't really use the time in this equation here, but we do use it as our bounds of integration. And we're also going to be using it to plot it, or as our x-axis here. So we're going to say t-plot is going to be linearly spaced. We're going to start out our time initial, go to our final time, And we'll say we want 1,000 points, make it nice and smooth. And then our H1, our H2, and our H3, which is going to be our y-axis, is going to be equal to the solution of solving that, solving our right-hand side using our solve IVP right here at each of these times. And then we're going to say figure equals make subplots. And then we want to go ahead and make our figures. So we'll say figure.add. Actually, we can just say fig.add scatter. And then we want our x to be our t-plot, our y to be our h1 array. And then we'll just leave it there for now, and then we'll come back and fancy it up a bit. And then same thing here, but we're going to be using our h2 array. And same thing here, but with our h3 array. And let's go ahead and just take a quick look at that. So there we go. We have our tank. This looks like our tank 2. Actually, I'm going to go ahead and label these because I'm not... No, this is our tank 2 because it starts at 1 meter. But we'll go ahead and label these. Not quite sure why it decided to name it like that. I'm going to figure that out, and I will be right back. So I went ahead and added in our set point here. The way I did it is, and this might not be the most efficient way, but it's the way that I did it. I just made a little list here that was the same length as our t-plot, and then using some list comprehension, I just set every element within set or our set point to 4, and then I went ahead and plotted it. And actually, I forgot to change the name here. So if we go ahead and take a look at it, you see when we zoom in, and just as a reminder, we changed our KC to a really high value, which let us see that we could overshoot by quite a bit. But if we take a look here, we can see that our height of tank 3, this green line here, oscillates both above and below the set point. So let's also modify our KC to be really small, I guess. And remember, just as a reminder, we started at 0.1. Now we're at 0.01. Looks like I need to run everything again because it did not quite pick up on everything. Oh, ignore that. I wasn't sure if NumPy could do that. It can't. So you'll see here if we have our proportional constant too small, all the tanks just drain out. So in reality, our goal would be to find some sort of proportionality constant that kind of meets in the middle where we want it, where either we wanted to get to the set point really quickly, or we wanted to get to the set point just really slowly. Because if we go back to looking at this as 0.1, I need to zoom out here. Maybe try running this again. Oh, duh. It just happened to look really similar. Or I just didn't notice. But anyways, if we have our set point too small, or our proportionality constant too small, we might never reach that set point. It's still increasing. It's just increasing really, really, really slowly. And actually, at one point, it starts draining, which is what we don't want. So in reality, our set point, or our proportionality constant, might be something closer to like 1. And as you can see there, we end up getting fairly close to our set point. But anyways, that's how we can go and find, or not find, but simulate a 3-tank system using process control proportional control dynamics.